Now, treatment of Gibbs free energy. How do we treat Gibbs free energy? Gibbs free energy is a measurement of the spontaneity of a reaction. Gibbs is typically measured as a relationship to enthalpy and the temperature dependence on entropy. Enthalpy and entropy. So we can measure delta G as delta H minus T delta S. One thing we must always watch out for is units when we do this, because delta G is typically given as kilojoules per mole. Delta H is typically given as kilojoules per mole, and because of it's the size of S, this is typically given as joules per mole, and then Kelvin. So that when we multiply Kelvin by joules per mole Kelvin, we get joules per mole. So we have to convert the two. But this comes back to the second law of thermodynamics that states that for a spontaneous reaction, so when a reaction is spontaneous, the entropy of the universe is increasing. We can relate this to another equation that says S of universe equals the S of the system plus S of surroundings. Now, S of surroundings is kind of difficult to measure, but we can measure S of the surroundings as in relationship to delta H of the system. So we can measure S of the surroundings as negative delta H over temperature, because the heat released by the system goes to the surroundings. And remember, entropy increases when temperature increases. So we can measure it as this. Once again, watch out for the units, because this needs to be in joules per mole Kelvin. So the best thing to do is to solve some of these guys. They are pretty easy. If you're given the temperature of 25 and you're given a delta G value, you can solve these by just taking the basic equation. Most of these numbers will be found by taking the sum of the products, which is our final state, minus the sum of the reactants, which is our initial state. Now, the same thing, we can use that to find our delta H, sum of products minus sum of reactants, and use that to find delta S. Now, if you have a book, you can find all this data. Yeah, you can find this data all where in the back of your book on Appendix C. You should be able to find this on the ebook. You can find this online. All the values there is CRC, which is a giant physics handbook that has a whole bunch of great knowledge in there. But so let's look at a hypothetical problem. Let's calculate at 55 degrees Celsius, what would this reaction be? Carbon graphite plus Cl2 gas goes to CCl4 liquid. So I would pull up my table. I'll show you this, where I'm going to pull the numbers from. So I'd look down here. You can read here carbon. Carbon S graphite has a delta H value of 0, a delta S value of 5.69. We're going to get CCl4 liquid. There's our delta H value. There's our delta S value. So I'm going to write these guys down. on a test type situation, typically we're going to be given these. So you won't have to memorize these. So CCl4, 139.3 and 214.4. Cl2 is, I'd have to look alphabetically, chlorine. Cl2 gas, 0 and 222.96. Notice, in this case, this is a pretty complex liquid, 214.4. But this is just a simple diatomic gas, but it has a pretty high entropy. If I'd gone with the gas version of this guy, the gas version of this guy would have been 309. So you can see the entropy increases greatly going from liquid to gas. So our delta H is going to be really easy. The sum of products, negative 139.3. How many of them are there? There's 1. Minus the sum of reactants. Well, 0 for graphite, there's 1 graphite. And 0 for chlorine, there's 2 chlorines. But 2 times 0 is 0. So our delta H value is negative 139.3 kilojoules per mole. Kilojoules per mole reaction. Our delta S value be 214.4 times 1 minus, we have 5.69 times 1 and 222.96 times 2. So this one is going to be, clearly we're going to lose entropy even though we're going to gain enthalpy. 69 and minus 222. Okay, so our entropy value is negative 237.21 joules per mole Kelvin. The last thing I need to do before I utilize our equations is turn our temperature into Kelvin. 55 degrees, we have to add 273 to get our value in Kelvin, so that's 328. So to find our delta G, we're going to take our negative 139.3 kilojoules minus 328 times our negative 237.2. But because that's joules, we need, there is 1,000 joules per 1 kilojoule. We need to convert that into kilojoules. Otherwise, we're going to overestimate the effect of our entropy. 2-1. So our Gibbs free energy, when all is said and done, is 61.495 kilojoules per mole. Really, if I rounded to sig figs, it'd be 61.5. 61.5. Now, doing that same value, doing that same thing, if I wanted to determine the entropy of the universe, I could use those same numbers. Let's write those down again. Negative 139.3 and negative 237.21. And our temperature is 328. So the entropy of the universe isn't really much different. The entropy of the universe is just a rearrangement and using these in a slightly different order. Universe. So in this case, we use our entropy goes first, and then we take a negative times our negative delta H. Since that's kilojoules, we have to turn that into, in 1 kilojoule, there's 1,000 joules. And then we divide by our temperature, 328 Kelvin. That's joules per mole Kelvin. So doing it the other way around will give us a slightly different number. But it will still have a relationship to the value, 328. So the entropy of the universe would be 187 point, we'll say 187.5. Well, it should maybe. That's joules per mole Kelvin. And that's a negative delta G relates to a positive entropy of the universe. We can do them both together. They are the same generalized thing. Now there's a simple fact that when delta H is negative and delta S is negative, or delta H is positive and delta S is positive, there is an inversion point. This is the last thing we'll talk about before we switch to a different topic. Inversion point. This inversion point is the point where delta G goes from negative to positive, or in this case, delta G goes from positive to negative. There's a temperature at which this value becomes too big, larger than the effect of entropy. There becomes a temperature where it becomes too big and we see a flip-flop of our values. So how do we calculate that? We can calculate that because the point where this goes from negative to positive is the point where delta G equals 0. So if delta G equals 0, we can solve that for our delta H minus T delta S. Rearrangement of the equation gives us temperature equals delta H over delta S. With that in mind, because that's in kilojoules per mole, and that's in joules per mole Kelvin, we have to keep in mind the units. But let's do that real quick. What temperature would this become non-spontaneous? So we take negative 139.3 times 1,000 joules in 1 kilojoule divided by our negative 237.21. That's joules per mole Kelvin. That's kilojoules per mole. Doing that, we'll quickly find out what temperature will that happen at. You do that, that temperature would be 587.2 Kelvin, which is 314 degrees C. So if I were to heat up the carbon and the chlorine gas to 314 Celsius, it would no longer be spontaneous. But those are the main aspects of Gibbs free energy and entropy of the universe. You find our delta H, you find our delta S, you turn temperature into Kelvin. If you've done those three things, you just need to watch out for the units and you plug it into one of the two equations, either the entropy of the universe equation or the Gibbs free energy equation, and then you'll find delta G. All you got to do.